All right, for those just joining, here I drew ray diagrams of different situations, including that one. So pause it if you need to look at those. All right, here, I'll leave this for you. It's not really a ton of math, but you can go through and use these similar triangles, set up your ratios, and start substituting. And what we can actually end up doing is getting what is called the mirror equation, which is also going to work for us for thin lenses. And that is it right there. Remember, the focus is half the radius right there. That's important. And then D naught is the distance to the object. So I guess that's not a naught, D sub 0. And then D sub I is the distance to the image. Anything in front of the mirror on the same side as the object, the shiny side of the mirror. All right. Essentially, the object's always on the front of the mirror. It doesn't make sense to put the object behind the mirror, correct? So the object, wherever the object is, that's the front side of the mirror. Anything on that front side, the same side as the object, is positive in its distance. Anything on the back side is negative for its distance in this equation. And then anything as far as magnification goes, if it's inverted, where it ends up below the principal axis, that's a negative magnification. If it ends up upright, that's a positive magnification. That makes sense? Maybe once we start using it. So anyway, there's the mirror equation. And then here are all the different outcomes you can get. Now, you can feel free to memorize this, or you can get good at drawing those ray diagrams like I was just doing. And you can usually, if you're good at them, you can sketch them in about, 5 seconds. It's really pretty quick to do once you get the hang of them. And then you just sketch it and you get all these answers. Notice here in this one, they don't talk about at F. They just do just beyond F and just inside F. So they didn't even go ahead and make mention of it in this book. Okay, so but a lot of times you'll see that where they say, like you can even see that right here, approaching infinity, just inside, just out. But right at the focus is usually called no image, so they didn't even put it here. All right, so essentially for a convex mirror, you get only virtual images that are upright and reduced. For the concave mirror, you see these same exact results we got. Beyond C, inverted, image size is reduced, and it's a real image. At C, inverted, same size of the object, which our ray diagram told us, and it's a real image. Between F and C, inverted and enlarged, which we got from doing a ray diagram, and it's real. We did just at F. So just before you get to F, it's staying that upside down real image, but it's very big. Like I said, it gets bigger, 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 and then you get to F and it becomes that blurry mess with no image. Then as soon as you go inside the focus there, it suddenly is upright and it starts to look good, and you see a nice virtual image inside of there between the mirror and the focus, okay? So it's up to you if you want to try and memorize all that, or if you just want to get good at understanding it with the ray diagrams, okay? And then I think here's the last thing, magnification. So what we have here for magnification is image height divided by object height. That's just basically definition, right? If your image is twice as big as your original object, your magnification is 2 times then, right? If your image is 2 times as big as, is twice as big as the original object and it's inverted, then your magnification is -2 because it's -2/1. And then you can also do this with the, it turns out that the image distance and the object distance will also, their ratio with a negative sign out in front of it, will also give you the magnification as well. Negative distance to the image divided by distance to the object. Okay, and that'll tell you your magnification. So let's take a look over here. I did this one already, so we're not going to do that one. I just did it a couple minutes ago, right? Use a ray diagram to find the size, orientation. So see lecture notes, maybe I should put. Or maybe I could just do this, right? What was that one? Where was it supposed to be? Between the mirror and the focal point? Here, I'll just do this. There you go. Okay. On the chart, it states that just beyond F, it's still inverted. So it's upright, it's enlarged, it's virtual. So this is in between it. This would be just inside it. This would be just outside it. They're like taking the limit as we go. Yeah, like a left and right limit kind of a thing. And they're doing that instead of saying, if you put it at the focus, you get no image. They're telling you this is what happens as you approach and then as you leave it, like as you're passing through it. Okay? All right, so next one here. After leaving some presents under the tree, Santa notices his image in a shiny spherical Christmas ornament. The ornament is 8.5 centimeters in diameter. All right, so we can go ahead and write that down. Diameter equals 8.5 centimeters. And 1.1 meters away from Santa Claus. So that would be our object distance, 1.1 meters. And curious to know the location and size of his image, Santa consults a book on physics. I mean, this is ridiculous. We know he wouldn't have to consult a book. All right. Knowing that Santa likes to check it twice, what result? Oh my gosh. What results should he obtain, assuming his height is 1.75 meters? And so then we'll say object height is 1.75 meters. So we have some stuff in centimeters, we have some stuff in meters. What would we rather work this out in? Meters? So what's 8.5 centimeters in meters? 8.5 times 10 to the negative 2 meters. Good. That's what centi means, right? Times 10 to the negative 2. All right. So now we first need to know where is his image going to appear. So before we do this, what kind of an image is it going to be? So let's write, what do we expect? CT. What do we expect? What kind of an image? Real or virtual? What kind of a mirror is this? Convex. Huh? So virtual. So we expect virtual. Upright or inverted? Upright. Enlarged or reduced? Reduced. Where do we expect it to be located? In front of the mirror or behind it? So behind the mirror. So these are what our expectations are. Let's see if the math tells us this. If not, then we know we've made some sort of mistake either in our understanding or in the math. Okay, so that's our physics up there expectation. So let's look at this. We need 1 over the focal, or well, let's do 1 over D naught or D0 plus 1 over DI is 1 over F. We don't have F. How are we going to get F? Okay, how are we going to get the radius? Half the diameter. So the focal length is what of the diameter? 1/4 of it. So we can make this 1 over D0, DO, 1 over DI is 1 over 1/4 of D, right? Which would just be 4 over D, like that. Do you want me to write the 1/4 in the denominator, or is that okay? It's 1/4. So we can say F equals 1/2 R, which equals 1/2 D. So 1/4 D. There you go.
It's written wrong on the initial, right?
Huh?
Okay. Wait, yeah. Because you just flipped it. Right?
Yeah, it was divided by 1/4, so I made it times 4. Okay, good so far? So now we need to find this DI. So I'm going to go ahead and start solving for DI and realize that I'm writing very big and running myself out of room. How do I resize this? Let me cut it and paste it, give myself a little more room. Okay, let's zoom in on this thing. All right, now we need to solve this for DI. So I'll get 1 over DI equals 4 over the diameter minus 1 over the object distance. Then DI will become, if we make these into one thing, this is D0. And so this is 4D0 minus D. And so this becomes diameter times the object distance over 4 times the object distance minus the diameter. Does that look okay? So our units, we have a bunch of distances there, right? A bunch of lengths. So in the numerator, we have a length squared, right? Length times a length. So we have a length squared. What do we have in the denominator? What units? And we can do that if we do a length minus a length, right? You can only add and subtract values that have the same units, right? You can multiply and divide whatever you want, but for addition and subtraction, they have to have the same units, and they do, because 4 doesn't have any units. So D0 or DO is length minus a length. So that gives us a length squared over a length, which is just a length, and we want a unit of a length, right? So this equation is at least dimensionally correct, right? And so now I can just plug some numbers in. What was the diameter? 8.5 times 8.5 times 10 to the negative 2 meters. D0 was 1.1 meters. All over, and then 4 times 1.1 meters minus 8.5 times 10 to the negative 2 meters. Anybody want to calculify that for us? Calculate? That's right. Calculate. Pretty sure that's right. Calculify. Calculification. Ning. Calculificationing. I'm pretty sure that's right. You can send me that email now if you want. I don't think anybody else is coming. Go for it. Thank you. So 8.5. So we should a little less than 4. Two.
I got 0.022.
I was going to say it should be about 2 to the negative 2. So what did you get? 0.022 what? Good. Meters. All right. So that's the image distance back on the back side of the mirror, which is the spherical ornament, right? So there we've got that. Now we need to find the image height because they gave us the object height, right? So we can look at this and we can say magnification is equal to image height over object height, which will equal oh, we're gonna do one quick thing here. This should be negative, right? Because because it's a spherical mirror like this, and our object is over here, and the diameter is on the backside, so the center is on the backside, so that should be negative. So we just need to put a negative in front of this thing, and then also make that a plus. So fix that real quick, please. See, that's why you got to think these things through, because I realized this should be on the back. It should have been negative. So when we started to do this, I remember their version has that negative sign in that equation. So we need to have this negative. So what does that turn out to be then? Change that to a plus, make this negative. Still not that different, but there you go. Okay. Negative 0.021 meters. There we go. And so then this is negative DI over DO, which wouldn't have matched had we left it that way. And so we're trying to find the image height. So height of the image is negative DI over DO times HO. And then the image distance was negative of negative 0.021 meters over the object distance, which was 1.1 meters, times the object height, which was what, 1.75 meters? Just like that. These will cancel out. And so what do we end up with there? Something small, 0.033. And that's a positive. That's positive for the image height because it is upright. And so there it goes. That works out nicely for us. So we ended up with a virtual image, correct? Because it ended up being object distance is in the negative side. So we got that. Virtual, we got behind because of that negative. We got upright because we have the positive magnification or the positive magnification, and we have the positive image height. And we got reduced because the image height is way less than his actual height. He's 1.75 meters, but his image in there is 0.033 meters. So 3.3 centimeters, pretty small. Okay? Totally lost? Sorry about that negative sign. Yes? Which, the magnification? There you go. Uh-oh, I see another totally lost face. It's hard to tell now because all I see are the eyes, but is it a look of panic?
Maybe a hint in there, but we're getting there.
Okay. One of the biggest mistakes I always make is forgetting negative signs. I get so careless with them. Please yell at me. Okay? Any questions on this one? Don't even know what to ask, or?
All right, so where did the negative sign come from? Just it was convex? Or?
Yes, since it's convex, you're talking about for the diameter here, it's convex. That puts the diameter on the back side of the mirror. So over here is negative stuff. Over here is positive stuff for mirrors. Notice I said for mirrors because we're going to have to make an adjustment to this when we get to lenses. Yep. Well, then you still would have used DI over DO, negative DI over DO, and then you would have found magnification, and then you would have, so in other words, you would have done this step first, and then taken that, and then like plugged it in over here for M, and then still had to multiply by that. So it would have been the same thing, just in a different order, right?
Well, I was just thinking like magnification, it's like a ratio of the heights.
Yeah, but you only know one of the heights,
Oh.
right? So we were trying to find the other height. So we needed that ratio, which we got from DI and DEO, right? So then you still would have had to have used that version of it. So. Any other questions? I like questions. I really do. I enjoy them. It makes me think y'all are actually listening. So then, perfect. I also like it when students get it. Doing okay over here or no? Want to see more? All right, what's the next one here? A dentist uses a small mirror attached to a thin rod to examine one of your teeth. When the tooth is 1.2 centimeters from the front of the mirror, so DO, 1.2 centimeters, the image it forms is 9.25 centimeters behind the mirror. So DI is what? 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 Negative 9.25 centimeters. There we go. Behind the mirror. Find the focal length of the mirror and the magnification of the mirror. So first off, all right, as soon as we do this, we're going to get a positive magnification. We know that, right? So we know that this is an upright image, and we know that it is virtual. We all agree? So far, just from looking at those two numbers, we know this is upright. We know it's behind. We know it is virtual. Is this thing enlarged or reduced? What's our magnification equation? Good, negative DI over DO, right? So if we're doing DI over DO, are we getting a number greater than 1 or less than 1? Or equal to 1? Greater, so is this enlarged or reduced? Enlarged. So now we need to say to ourselves, what kind of a mirror can give us an enlarged virtual image? So you can look here at this chart if you remembered it, or we can look back here at our examples, right? If we have this one always gives us a virtual image, so you might be tempted to say that, but what do you notice about the images? They're reduced. So this one isn't going to work. So we come back over here. That's real. That's real. That's real. Hey, right here, we didn't even write it. Sorry. This is virtual, enlarged, upright. It's behind the mirror. That's all the properties we have right now, right? So what situation do we have? We've got that one. We have a concave mirror, right? This is a concave mirror. So we have magnification greater than 1, right? So this means concave. I got therefore concave, okay? So these two things tell us greater than 1. So that's what we have right now. So let's see if we can start doing this math. So first we need to find the focal length. We can do that with 1 over D0 plus 1 over DI equals 1 over F. That's our mirror equation, right? If I combine these two together, I'll get DO times DI over DI plus DO equals F. So taking the reciprocal, combine those into one fraction, and then took the reciprocal. We all agree with it? The common denominator is dO times DI, right? So I multiply this one by DI over DI, and I multiply this one by DO over DO. Correct? Okay. I see like one person nodding. Is everybody okay with that or no? Should I not be skipping this math? It's not math class, right? Try and do that math on your own. You got to get good at these little algebra things. All right. So now that's our focal length. We just have to plug numbers in. Okay. We're getting low on time, so I'm going to leave you to plug those numbers in. Plug in numbers. In other words, plug those two numbers in. Be sure to include that negative sign. All right. And you will get a positive focal length here. You should end up with a positive focal length since this is a convex mirror, correct? So when you do this, you should end up with that, which is going to make sense because both the numerator and the denominator here will both be negative numbers because DI is negative. And so that makes the numerator is a negative times a positive. That's going to be negative. And then in the denominator, you have a larger negative number plus a smaller positive number. That's going to make a negative number. So you should end up with a positive focal length here, which is what we would expect for concave mirrors. Okay. And then the magnification, well, we pretty much just did that. I erased it. Magnification is negative DI over DO. And you can just plug those numbers in. Negative 9.25 centimeters over 1.2 centimeters. You want me to write the plugged in numbers here? Here, y'all can do that. I'll write it. How about that? This is going to be 1.2 centimeters times negative 9.25 centimeters over negative 9.25 centimeters plus 1.2 centimeters equals F. So y'all can calculate those things up. Huh? Is that what it turns out to be? Awesome. Okay. All right. Any questions on this one then? A little better after the second one than the first one? Okay, so try to know those properties, try to think through, figure out what you're going to expect, and then see if the math fits. If the math doesn't fit what you expect, then you either messed up what you should have expected or you messed up the math. And like I did on that first one where I left that negative sign out. All right, and you got to get good at that because again, nobody's perfect. I'm going to make mistakes, but the big difference is how quickly I catch those mistakes, right? I usually catch them pretty quick because I start thinking, does this make sense? Does this make sense? Constantly ask yourself if what you're doing and the answers you're getting or the answers you're about to get make sense. If they don't make sense, go back. Either your understanding is messed up and therefore the answer does make sense and you just think it doesn't, or you've messed the math up because they should match. It's a very incredibly impressive universe that God has made for us and it matches, right? It's amazing this all works and it all works so well. Okay. All right. And then on this one is, oh no, this one goes with the next part. That's right. I remember looking at it. All right. So we got a few more minutes here. Let's keep going. So we did this. This was our mirror equation. So again, in front of the mirror is positive. In front of the mirror is wherever you put the object, right? It makes no sense to put the object on the back side of the mirror. Everything on the front side of the mirror is positive. Everything on the back side, including the focus and stuff, if it's a convex mirror, those are negative. For image distances and focal lengths, the object distance is going to always be positive. Otherwise, you don't really have a situation where the light can reflect. And then anything upside down is negative for magnification. Anything upright is positive for magnification. Okay, we looked at that. Here was our magnification. Make sure you know that. And then here is all that stuff I was just talking about. Again, you can memorize these or just think about it. Is it in front or behind the mirror? Is it upright or inverted? In front of the mirror, positive, behind the mirror, negative, upright, positive, inverted, negative. That's all this is telling you right here. And again, with single mirrors or single lenses, anything that's upright is virtual. Anything that's inverted is real. Okay, so again, comprehend or memorize. So memorize that previous table or understand the ray diagrams, or understand where location, how location determines positive, negative, or memorize all this stuff here. I don't know about y'all, I am not big on memorization. All right, so the next thing this moves us into is we're going to start talking about light moving from different mediums. This is now going to become refraction instead of reflection. So we finished with reflection and we're getting into refraction. Anybody ever seen where you're on the other side of a door and there's a light inside the room and the door is just slightly cracked open? Right? You ever seen that? And the light spreads out. All right, this is the kind of stuff we're going to start looking at now, where we're not looking at it just reflecting, but it bending as it does different things and goes from one place to another. In particular, we're looking out here is the refraction version when it changes mediums, when it goes from one medium to another. Now we talked about sound, and sound changes speed when it changes mediums, right? So what is sound faster in, this wall or in the air? The wall, right? And since one of the very key things about that is the frequency doesn't change. All right, so what changes is the speed and therefore the wavelength. But we're interested in that speed thing here. So when we're looking at this, when light goes through here, it actually is going to start to bend. Okay, and the reason it bends has to do with that frequency change. It's a little more complicated than this. We're not going to get into all of that. We're not going to get into, it's like this superposition of waves based on frequency changes type things. What we're going to instead do is we're going to look at barrels rolling. Okay, so let's pretend here that we have grass there on one side, and then over here it's concrete and grass. Now, if we're trying to roll a barrel, is it going to roll faster through the grass or on the smooth concrete? Smooth concrete, right? So you can imagine if I had a barrel, and again, this isn't technically the correct thing. This model has some flaws in it. Well, let's say I had a barrel like this, and I rolled the barrel at an angle towards the grass, and then both sides of the barrel are rolling at the same speed like that. All right, and let's pretend that as soon as it hits this over here, right, so our barrel gets over here, right, this is our barrel. This speed over here in the grass is still going to be the same. But now the part of the barrel that's on the concrete can do what? Roll faster. So its speed is going to be bigger. What's that going to cause it to do? Turn, right? So this thing was coming in this kind of a line, and now it gets here, it gets on the concrete, and it's going to bend like that. It's going to change directions. And the same thing in reverse. If we were rolling it the other way, then we'd have two fast ones, and the side that got onto the concrete, so like if we were going the other way, this side would slow down while this side was still fast, and it would turn the other way. It would go from like this into that. So if you notice, when this barrel rolls from a low speed to a high speed, it's going to bend away from the normal. When it goes from high speed to low speed, it's going to bend toward the normal. All right, and this is also going to turn out to be true for light. When we send light from a medium that is high speed into one that is low speed, it's going to bend toward the normal. When we send it from low speed into high speed, it's going to bend away from the normal. Okay, and we're going to take advantage of that coming up here in the next class. Okay? Y'all, you have a question?